The first pulley weighs 5 kilonewton and is placed at 1 meter to the right of left support, and the other pulley is 10 kilonewton and is placed at 1 meter distance towards the left of right support. Find the diameter of shaft if the bending stress is to be limited to 50 megapascal. What will be the size of a hollow shaft if the outer diameter is same as solid shaft? Okay, so this is the numerical given. Now, before we start, first let us find the maximum bending moment on this shaft. Now I can assume this shaft as a simply supported beam of length 4 meter, and that is carrying 2 point loads 5 kilonewton and 10 kilonewton, right? So let us draw the beam first. So let us say this is my 4 meter beam, right? And I have end supports like this. So I have one support here and there is another support here, right? And he says there is two pulleys on this shaft which are weighing 5 kilonewton and 10 kilonewton, and they are placed on this shaft. So that will act as a point load. So one of the pulley, it is acting at 1 meter distance to the right of left side. This is left side support. 1 meter right side is here. Okay, I'll just move it a bit more. And there is one more. I'll show it a little larger because this is 10 kilonewton, and this is at 1 meter to the left of right support. This is right side support. Left side of right side support is this. Now let me just write the values. This is 5 kilonewton. This is 10 kilonewton. I'll name the points. This is A, B, C, and this is D. And I will also show the lengths. Okay. Should be fine. Now this is 1 meter, this is 1 meter, and the total length is 4, 4 minus 2, so this is 2 meter, right? So this is the arrangement of the beam that is given. Now I need to find the maximum bending moment. So for finding the maximum bending moment, I will have to first find the support reactions. So for finding the support reactions, I will take moment about A, taking about A. Uh, from here we will start. So I have reaction here. MA is equal to RA into perpendicular distances 4, so into 4. Other two will be minus, it is downward, minus 10 into perpendicular distances 2 plus 1, 3 minus 5 into 1, right? And this should be equal to 0 because this is end support, the bending moment there is 0. Now when you solve this, you get RA. Uh,
Sir,
and yes,
sir, we are taking moment about A. So RD will become na.
yeah, sorry, I wrote RA, is it? Correct. This is RD, not RA. I was thinking RD and I wrote RA. I'm sorry. Yeah. RD is 10 into 3 plus 5 divided by 4. So 8.75 kilo Newton. And sum of all the forces should be equal to 0. So RA plus RD is equal to 5 plus 10, which is equal to 15. So RA, sorry, I wrote 10, 15 kilonewton. RA is 15 minus 8.75, that is RD. So 15 minus 8.75 is 6.25. This is 6.25 kilo. All these things is same what we have done in our uh, previous unit, right? Shear force and bending moment diagram. We have done all these things already. Now I have to find the bending moment. So BMA is equal to BMD is equal to 0 and supports. Now BMB is equal to, at this point, here I have two force. On the left side I have only one force. So I'll take left side. So it is RA, I'll write the value directly. RA is 6.25 into perpendicular distance is 1. This is 6.25 kilonewton meter. Then BM C is equal to, left side I have two force now, right side I have only one. So I'll take right side. That is RD 8.75. So 8.75 into 1, which will be 8.75 kilonewton meter. So from this, I know that the maximum bending moment in this beam is 8.75 kilonewton meter. That is acting at point C, right? See, if it were to be a UDL and point load combined together, then we have to find the location of maximum bending moment. That will become little complex. So in this numerical, it is very simple for us. Directly we got the maximum bending moment. Now we can find the diameter of the shaft. Now before finding the diameter of the shaft, uh, I'll first write the bending equation. Now what is bending equation? Bending equation, we have bending stress is equal to my by I, right? M is bending moment, maximum bending moment on the beam. Y is the distance of farthest fiber from the neutral axis. I is the moment of inertia about the neutral axis. Now the cross section for the first case that is given is a circular cross section, right? This is the cross section, and this diameter I'm taking it as D. Okay, I'm taking this diameter as D. Now I have to first find the uh, this diameter D. So how to do this? Now in this equation, I know the bending stress. The permissible bending stress for this shaft material is 50 megapascal, right? It cannot increase more than 50 megapascal. So I will use this value as 50. This will be maximum bending moment, which is 8.75. Y will be d by 2, and I is moment of inertia. There is also another formula. This my by I is equal to m by z. What is z? Z is the section modulus, right? So we will find section modulus, and from that I can find the diameter. Now let us find the section modulus, or z is equal to m by, I'm not able to write sigma in paint, so I have to write it as bending stress. Now the bending moment is 8.75 kilonewton meter. So I have to convert this into Newton millimeter. So there is 1000 here and 1000 here. So it will be 10 raised to 6. So 8.75 into 10 raised to 6 by 50 megapascal. So this will give me the section modulus Z, 8.75 into, sorry, 6 is to 10 into 8.75 is this by 50. 175,000 is the section modulus. Unit will be mm raised to 3, right? This is not volume, but this is section modulus, moment of inertia divided by distance of farthest fiber. Now the section modulus for circular cross section we have discussed yesterday, pi d raised to 3 by 32, right? I is pi d raised to 4 by 64 divided by d by 2, so it becomes pi d cube by 32, correct? Now that value is 175,000, so from this I can find d. So 175,000 is equal to pi into d cube by 32, or d is equal to this into 32 by 5 is this, cube root of this is 121.25, right? So this is the diameter of shaft that is required for this particular beam. Okay. Now there is an extension to this question. What will be the size of a hollow shaft if the outer diameter is same as solid shaft? That means I have to keep the outer diameter same as this and find the inner diameter of the hollow shaft, right? So I will continue on this side here. Okay, so now you don't have to calculate all this again because I have done already. See, the section modulus needs to be same, right? Section modulus will not change for getting this much of bending stress. Only this formula will change, right? So let us try to find this. First, let me draw the cross section. So I have a circle like this, and then hollow circle like this, right? So this is the shaded area is the actual cross section of the hollow shaft now, right? I'll just name that. This is D, and this is small d, right? So this I'll take it as capital D. This I'll take it as lowercase d. Let me just quickly open the PPT that we saw yesterday. Yes. So the section modulus for hollow circular section, you can see the slides. We discussed about this yesterday. How did we get this? I is pi by 64, d raised to 4 minus d raised to 4. Y max is capital D by 2. Z is I by Y max, pi by 464, d raised to 4 minus d raised to 64 by d by 2. So when you simplify this, you get pi by 32d d raised to 4 minus d raised to 4. So by using this expression, I can find this d. So let me just quickly copy this equation so that it's easy for me there, right? So I have section modulus for this hollow as this. Now this value will be 175,000 again. 175,000 is equal to pi by 32 into D is 121.25. See, this is millimeter to the power of 3 only. So I need to put everything in millimeter. 121.25. This is pi by 32D into D raised to 4, that is 121.25 raised to 4 minus D raised to 4. So this implies D is equal to how much? Please try on Calci if somebody can do this quickly. I'll try it here. So this will be pi by 32 by 121.25. This divided by 175,000 is this much, and that is equal to this minus this. Now this will come over as I made a mistake. 175,000 into 32 into 121.25 by 5 is equal to 121.4 raised to 4 minus this. So this I will copy and 21.25 raised to 4 is this minus of this. Oh my god, getting it as negative. Did anyone get the answer? Here I kept my calculator. Just doing in this will take.
Hello, sir. Your voice is getting cut.
Yeah, anyone got the answer for this? I'm just trying to use my calci. 175,000.
Hello, sir.
Yes,
So I got around one.
one.
Yes, sir.
I don't know. I did not solve this. I just made this numerical right now. 5 into 1
Got 36.01 answer.
36.01 possible. Uh, just a minute. I'm just trying in my calci. 32 into 121.25.
So 34.59.
Hey, how can be so much mistake? 3527.04. I'm getting 7.7. 4. I'm getting 7.7. I don't know. How much you got? 34? Hello?
34.59.
0.59 mm. Right? So around this you must be getting. So now what you need to observe here is, see, in case 1 and case 2, I have not made any change in the load, right? The span, the load, everything is same. What is the change I have made? I have changed the solid shaft into a hollow shaft. So now what is the advantage, you may ask, right? So the advantage in doing this is I have reduced certain amount of weight, right? Now this cross section area is reduced by how much? Let us quickly check. Earlier it was uh, pi into 121.25 square divided by 4. So initially the area was 11,546 millimeter square. Now the area is decreased and the area has become minus 34 if I take. Now the area is 10,638, right? So how much is the reduction? Almost 1000 millimeters, right? About 10 to 12% of the cross sectional area is decreased. That means I have decreased the weight of this beam by 10 to 12%, right? So this is the reason, if you see any large truss, right? For example, if you go on highways, you will find this toll plazas. So the roof of the toll plazas and all the columns and beams, everything that is used, they don't use solid anywhere. They always use hollow sections, right? It can be a rectangular hollow tubes or circular tubes, or it can be square tubes. Any sort of tubes are used, but not solid rods, right? So the section modulus plays a very important role in the bending. Okay.